The first speaker is Tomaž Prosen from Ljubljana. The title is Random Matrix Spectral Fluctuation in Quantum Lattice Systems.
It's on now, yeah. Okay. Yes. Good afternoon. So, yeah, it's a pleasure to be able to speak in this very elegant and nice environment. Also, it's a challenge to speak in such a kind of broad audience, and probably my talk is not going to be really along the mainstream of this conference, but still, I think it could raise interest of some people. So I try to be as pedagogical or as illustrative as I can. So maybe to connect my talk a little bit to the previous talks, I would say it's about, let's say, chaos. So in that sense, it's maybe close a little bit to the talk of Viviane Baladi. And it's about quantum lattice systems, so it's a bit close to the talk of Ogata. But anyway, it's about combination of the two concepts. So as you see, I mean, these two concepts have not been kind of brought into connection very much in the literature. So that's the reason why I'm kind of excited about this, so to connect chaos with quantum lattice systems. Okay, so now just to give you sort of my motivation and outline for the talk. Yeah, you heard about very simple class of models that mathematicians can tell us a lot about, this Sinai billiards. There are even simpler models in dynamical systems theory, which are like textbook and pedagogical material for teaching courses in nonlinear dynamics, like Baker maps and cat maps. So models that you can solve on the blackboard in half an hour, computing correlation functions and all that. But if you look at textbooks in many body physics, you don't find such models. I mean, you find free systems, you find integrable systems, but you don't find exactly solvable, non-integrable, strongly coupled systems, like chaotic systems. And the main motivation for my talk is to present you with a class of such models for which we can compute a lot. And yet they are strongly coupled and non-integrable. These are the two heroes of my talk, Bruno Bertini and Pavel Kos. Bruno was a postdoc and Pavel Kos was a PhD student who basically worked on all the stuff that I'm going to discuss. But okay, so let me start with some very, very old kind of historical motivating slide. I mean, someone mentioned in the talk, in the question discussion, in the question time of Baladi, someone asked about quantum features of chaotic systems. And I think there was a statement that this is a big business. Indeed, it is a big business since the 1980s. So people have been curious about what is the corresponding features of quantum models, which are classically, supposedly that they have classical, semi-classical limit, which are classically chaotic, hyperbolic, if you want. This is the so-called Bohiga's conjecture or quantum chaos conjecture. So people have established that even very simple models, which are classically chaotic, should have statistics in quantum mechanics. When you quantize them, for example, you compute energy spectra or eigenfunctions, their statistics should be given in terms of ensembles of random matrices. I mean, the idea which was pioneered into physics by Wigner in the context of nuclear physics has been further simplified, and people understood by mid-1980s, or at least they conjectured that these structureless ensembles of random matrices should excellently describe statistics of simple models which are hyperbolic. I mean, this is just an example of level spacing, the so-called level spacing statistics for an integrable billiard circle and a chaotic billiard Munimowicz stadion. And you see there is a dramatic difference, and the spacings for chaotic billiard are described by GOE distribution which is obtained from random matrix theory. I'm not going to discuss level spacings in my talk, but just this is the most simple, I mean, at least easy to compute measure of spectral correlations that we discussed. Please, if there is a question, please interrupt me during my talk. I understand that some of the concepts are very new to most of you, so please ask anytime you're curious about or something is not clear. Anyway, so you know, my talk is not about numerics, numerical experiments. It's not about single particle problems. This is just a motivation. My talk is really about some very simple but rigorous statements about quantum lattice systems. So let me move on. So what I'm going to discuss is theoreticians' favorite measure of spectral correlations, which is a two-point spectral function, or its Fourier transform, the so-called spectral form factor. And I'm going to discuss maps. Again, I remind you of the talk of Viviane Baladi. I mean, she discussed flows and maps. Flows are like Hamiltonians, and maps are like Poincaré maps or stroboscopic maps. Or in this context, people usually call those systems Floquet systems. So they are given like time periodic driven Hamiltonians, which you can integrate over a period of time. Then you get a time ordered propagator. Imagine you have a finite system. So the idea is to forget about field theories, forget about infinite systems. For the moment, let's think of a finite system. So a spectrum is a set of points on a circle. This is a unitary operator. The spectrum is a set of points on a circle. I call them quasi-energies, phi sub n. And they define a distribution of which is supported on a unit circle, which we denote as a spectral density. And then define the simplest possible correlation measure of spectral density, which is the two-point density-density correlation function. You integrate it over a circle because you assume that there is democracy over a circle. So you assume there is no preferential point. There is no ground state in Floquet systems. All states are kind of equivalent. So you define a totally democratic two-point function, which only depends on a single variable, which is the distance between two quasi-energies. And then you do the Fourier transform of that. And that's what is known as spectral form factor. So again, it's a pure two-point measure. It's a pure two-point function. Imagine now your spectrum is a gas in 1D on a circle. Now this is its two-point function or its Fourier transform of the two-point function. Since it's a Fourier transform, the Fourier variable is integer because it's a Fourier analysis on a circle. So Fourier variable is an integer, and this integer has a meaning of time, namely number of repetitions of your Floquet property. And it's the Fourier transform, I mean, the spectral form factor itself is just, you know, this is a trivial calculation, is given by the trace of the propagator to power t modulo square. So you have to have two copies. So that's why it's a two-point quantity. So you have to have two copies of the propagator. But you know, the main thing is that this is formulated purely in terms of the trace of the propagator. So there is no dependence on initial state. There is no dependence on any observable. It's a pure, you know, it's a quantity which only depends on the propagator. So it's the minimal dynamical information that you need in order to address this quantity. Okay, now it's nice, it's elegant, but it also has a caveat. This quantity is very hard to compute because it's not self-averaging. I mean, it doesn't make really, as it is written, it doesn't make much sense. So one has to do, in addition to that definition, one has to introduce some sort of this random parameter in your model or some parameter, and you have to average over that parameter. I mean, you can do even weaker forms of averaging. For example, you can do moving time averages, but the quantity as it is known in random matrix theory, but also in dynamical systems, this quantity is not self-averaging, so we have to introduce some sort of averaging in order to make it mathematically meaningful. Anyway, I'll be precise later on what I mean by averaging here. But let me just first tell you what random matrix theory tells us about this two-point function, the spectral form factor. I mean, there are closed form results in random matrix theory, in particular for infinity dimensional matrices or high dimensional matrices. My matrix dimension will be usually denoted as curly n. So for matrices which have no structure, I mean, just represent quantum dynamics, that is unitary. For that, one has to apply Dyson circular unitary ensemble, or just UN if you want. This is just unitary group with a Haar measure. When you have a time reversal symmetry, then you have to apply the so-called circular orthogonal ensemble, which is again obtained from a unitary group, but with this particular construction I'm not going into. But again, there is a closed form result from random matrix theory which tells you that the spectral form factor grows like linear function of time until it hits the so-called Heisenberg time, which is given by the Hilbert space dimension, and then it saturates. So this is the unitary ensemble. Orthogonal ensemble gives us slightly or twice larger growth, 2 times t, but then it has a smooth connection to the saturation, which is given by the Hilbert space dimension again. And then one has to compare this to total random spectrum. I mean, it's kind of interesting. I didn't tell anything about this, but There is a complementary conjecture to this Bohigas-Janones-Schmidt conjecture. There is the so-called Berry-Tabor conjecture, which tells us what happens in integrable systems. In integrable systems where there's lots of structure, spectrum is random. I mean, it's kind of curious. In chaotic systems, when there is no structure, spectrum is rigid, is correlated. In integrable systems where there is a lot of structure, which allows us to order eigenvalues by quantum numbers, there is no correlations among levels, among neighboring levels. And this is characterized by the so-called Poisson ensemble or Poisson statistics, which tells us that the form factor should be just flat. So see, if you want to compare, now if you are really interested in modern day experiments with emerging quantum technologies and quantum simulators, I mean, you might soon be able to do some experiment along this line because, you know, if you are able to measure somehow the spectral form factor for short times for, let's say, a many-body system where Hilbert space dimension is 2 to the L for L qubits, then you see that there is a huge gap between T and 2 to the L for short times, right? So there, you should be really able to see this integrability versus non-integrability in spectral form factor. I mean, that's sort of my experimental motivation. I mean, we are really kind of at the advent of these quantum technologies, and I think they should be kind of really able to address these questions of quantum many-body chaos in the way I'm discussing here. Anyway, so now there is, of course, I discussed a little bit about timescales. There is this Heisenberg time, which is kind of totally obvious. It has to do with level spacing, mean level spacing. So when a time is longer than the level spacing between adjacent levels, then basically these phases which enter into the definition of the form factor, there should be a time t in front of exponential here, which is missing. I'm sorry for that. But you see, when time is of the order of number of levels, then this distance becomes of the order of 2 pi, which means these phases become pseudo-random, which means there could be no correlations afterwards. So this is explanation why things should saturate 4 times longer than Heisenberg time. So there is this absolute longest time scale up to which quantum dynamics becomes quasi-periodic for any sort of spectrum, discrete spectrum. But you know, there is another time scale which is much more interesting from the point of view of physics, which is usually referred to as the Thouless time, which has to do with the transport phenomena like diffusion. For example, in systems with conserved quantities, there is diffusion, and one expects that there is a time up to which system explores the allowed space, which is usually scaling like square root of space. Let's say t is proportional to L square over the diffusion constant. So this is the so-called Thouless time, and below this Thouless time, system cannot be described by random matrices. There should be some model-dependent, I mean, model-specific dynamics, and spectral form factor cannot be universal. So what people expect is that there's a universality regime between Thouless time and Heisenberg time, which should be described by random matrices. Now, I should tell you immediately, the model that I'm going to discuss, this, well, I mentioned it a couple of times already, but I have not yet defined it. But the model I'm going to discuss is actually really cool, because for that model, there is no Thouless time. The model will be described by random matrices from time 0 onwards. It's a kind of critical model. I mean, there is no scale apart from the Heisenberg time. So that's why we can actually do some calculations. Anyway, so, but before going into the many-body context, let me just spend one slide to tell you what has been actually accomplished in single particle physics. I mean, that was, again, the big business that was mentioned on Wednesday. In 1980s, 1990s, and 2000s, the whole community of the so-called quantum chaos at the time, I mean, these days, quantum chaos, you know, is understood slightly differently because people from high energy and string theory have entered the game. So now it's become much broader. But in the old days, quantum chaos was really about single particle problems. And there people were really curious how to derive spectral form factor from semi-classics, that is from short wavelength approximations or limits of the quantum propagator, that is the Feynman, if you want doing the stationary phase on the Feynman path integral. For example, you can compute the propagator. I already showed you that spectral form factor is just the propagator modulus squared, right? So then the propagator you can write in terms of path integral and do the stationary phase for small h bar. You obtain something which is known as Gutzwiller trace formula or Gutzwiller semi-classical sums, which expresses the propagator in terms of sums over periodic orbits. So 2 propagators means double sums. And then people have discussed, you know, the cancellations in this double sum, right? There has been like 2.5 decades of progress really about, you know, understanding of cancellations or correlations among classical periodic orbits. And that, I mean, really the problem of understanding why random matrix theory is so successful in describing quantum chaos was about understanding why there are no correlations or what controls correlations among classical periodic orbits. For example, Berry was the first who basically pointed out that already in '85, that if one just does what is the most naive, the so-called diagonal approximation, then form factor should already display this linear ramp for short times. So the leading term of random matrix theory is already there simply by doing the most naive random phase approximation. But then much harder was to be able to understand the details about high order terms. And one has to wait 16 years before Sieber and Richter had proposed the second order terms, which had to do with the complex periodic orbits with complicated topology, or orbits which perform some sort of self-encounters in classical phase space. That was the second order term in 2001. And then in 2004, in the group of late Fritz Hake, Sebastian Miller, who was his last PhD student, was completing this program, providing the full combinatorics of the expansion of spectral form factor in H bar, and giving the full, let's say, diagrammatic expansion of the random matrix spectral form factor. I mean, it's like you take this was for systems with time reversal symmetry, so expand this in power series around 0, and all the terms are given as sums over periodic orbits of a given topology with respect to these self-encounters. So that was actually a really nice success. But one has to stress that this is not a rigorous mathematical physics. I mean, this is nice heuristics, but so far there are still no theorems. I mean, it's still not clear what about the rest of periodic orbits. So, I mean, just, before I go to many-body physics, I want to stress that there is still work to do to understand even a single particle quantum chaos. But now, I mean, my talk is about many-body physics, and my talk is also about non-perturbative, let's say, systems where there is no small parameter, where H bar is of the order of 1. So again, here we have a lot of phenomenology, which tells us again that simple models of many particles, let's say with local interactions, like these spinless fermion models, this is a canonical model in this field we will study. One dimension, canonical fermions, nearest neighbor interaction, next to nearest neighbor interaction, next to nearest hopping. Now, if there is no next to nearest terms, this model is equivalent to Heisenberg XXZ, so it's integrable. So the level spacings are like Poisson. When you introduce next to nearest neighbor couplings, then you basically go, with a fixed system size from Poisson to random matrix quickly. I mean, this has been a kind of phenomenology which has accumulated in the community, beginning, let's say, in solid state community, but later, I mean, this new emerging community of non-equilibrium dynamics since early 1990s. And it's become kind of definition of quantum chaos. I mean, if you go to conferences in this field, people would have, spoke about quantum chaos, but what they mean really is that, spectral statistics is Wigner Dyson. So there is, right, I mean, so how would you explain that? I mean, you have this is about Hamiltonian, for example, but you have a Hamiltonian which has a very simple structure. I mean, it's a 1D Hamiltonian. It's defined on a tensor product of two-level systems. So if you want 2 to the L dimensional Hilbert space or Fock space of fermions. But I mean, it's highly non-random. I mean, there are only, let's say, of the order of L, this 2 to the L dimensional matrix, but it's only of the order of L non-zero elements in each row. And these are highly non-random. They are given only by 4 possible values of coupling constants. So, this is a very simple, simple Hamiltonian with lots of structure. I mean, with a very rigid structure, with very, very little randomness, which has a spectrum which is described by random matrices. So it's, very far from the intuitive idea of Wigner, who proposed to use random matrices in physics, yet random matrix theory works brilliantly. So how do we explain that? I mean, that's, to me, it was like a question which started puzzling me soon after my PhD in mid-90s. And I'm very happy that, after 20 years, we were able to find, really first rigorous results explaining this, I would say, unreasonable effectiveness of random matrix theory in many-body physics. Anyway, so now this is already about the model that I'm going to present, but this is just, again, some numerics from almost 15 years ago with my student at that time, Carlos Pineda. we looked at spectral form factor in the model that I'm going to flash to you in the next slide, which is the so-called kick-teasing chain, which is kind of a minimal model of interacting quantum spins. Now, this is just to show you what does it mean that spectral form factor is not self-averaging. I mean, this ascent graph here is what you get if you just compute spectral form factor from definition. And this black line behind is what you get when you do just moving time averages. This is for the system of 19 spins. So it's several 10,000 levels. But if you do moving time average, so the Heisenberg time is of the order of, again, several 10,000, but the moving time average over a window of time of 100 steps is already enough to get a smooth curve, and this smooth curve brilliantly agrees with random matrix theory, which is the red one. So that was, again, just to the point numerical evidence that we should have also quantum chaos in this kicked spin model. And one had to wait again for another 15 years, for 15 years maybe, or a little less, but until 3 years ago, we came up with sort of first, let's say, results which were explaining qualitatively or heuristically at first why random matrices work for many body systems of that type. There were two type of two kind of papers appearing almost at the same time. There was a paper from our group, and there was a paper from Oxford, from the group of John Chalker, who looked at slightly different perspective. They looked at quantum Floquet circuits. So that is locally interacting qubits, or qubits of dimension q. And they had to let this q to infinity, so they had a small parameter. That's not exactly what I want, but still, I mean, they were able to confirm validity of random matrix theory. Anyway, so right, so now really what I'm going to discuss in the rest of my talk is spin 1/2 systems or spin lattices with q equal 2 with strictly local interactions. So the model that I'm going to, again, I'm going to refer to a very nice remark by Viviane Baladi on Wednesday, when somebody again asked about I mean, it was a discussion session and someone asked, I don't know, about applications of this nice mathematics, and her answer was that, she doesn't care so much about applications, but she's educated in the spirit that, one should care about beautiful models. And again, I very much share this kind of point of view. I mean, yeah, it's, when you have a beautiful model about which you can say a lot, I mean, this can later teach you about applications and generalizations, but let's first understand some particular beautiful model. And I want to argue that this is a kind of model like that. So this is, I will now go to precise definition of the model. It's basically, it's like a classical spin, classical Ising model in 1D with a longitudinal field, which is at this point allowed to be side dependent, random. But then on top of that, you kick it with the transverse field. So then it becomes quantum. So this model is like a two-step protocol, or if you want time-dependent Hamiltonian, where you have free evolution, which is the classical Ising model, and then have kicks, which is transverse field. And if you write time evolution map, this is the Floquet propagator, is just a composition of two exponentials. And of course, remember, these two exponentials don't commute, so you cannot write them. I mean, if you want to write them using Baker-Campbell-Hausdorff, this will result in some non-convergent, horrible series, and you don't want to do that. So it's better just to think of it as a composition of two simple strings of quantum gates, if you want. I mean, these are like single qubit quantum gates. These are like interactions, 2-qubit quantum gates. Okay. Now this model is integrable in the special cases when there is no transverse field or no longitudinal field. But when both fields are present, this model has basically no symmetries, and it is presumed to be quantum chaotic. And okay, as you see, I have already introduced magnetic field, longitudinal field, which was side dependent. So that's how I will introduce disorder, because I will have to average over some parameter, and the perfect averaging, which I want to do, is the disorder averaging. So I will introduce this HJ as IID random fields. So independent, random, identically distributed fields, which I will assume for the moment to be just Gaussian distributed. I mean, this is just to, again, give you some numerics. And in this business, usually it's very kind of convenient to start with doing some numerical experiments just to see whether you have the right setup. And this is just to show you that this is indeed the right setup. So this is, this is the way how we precisely define. So this IID Gaussian random fields with average H bar and variance sigma. And in this K of t is just trace of u to the t modulo square, as I already showed before. And for special values of J and B is equal to pi over 4. So these are like, if you want, strongest possible couplings, because these are coupling parameters in my model. When J and B are small, then this can be approximated by a continuous time Hamiltonian, which is, well, maybe not integrable, but still, maybe it has different physics. And when J and B are large, again, this is almost, free in some sense. The sort of the hardest case, or the most strongly coupled case, is when J and B are of the order of pi over 4. Okay, now, and for that values, pi over 4, this is, again, I'm going to discuss in the next slide why this precise pi over 4 is important. The spectral form factor for 15 spins has a beautiful ramp with a slope which is equal to 2. Now these are different system sizes, and you see that for short times there are some finite size effects, which are these noise fluctuations, but these are really finite size effects. So if I increase the system size, these go down. And well, I'm just going through going straight to the theorem that we can prove. So what we can prove for this system in particular is that for odd times, the disorder average spectral form factor, this is the K bar, the disorder average spectral form factor, is equal to 2t precisely for t larger than 7, and 2t minus 1 for t less or equal to 5. And for even times, the model is in different universality class. So the problem is, in 5 minutes, I will simplify the set of models even further. So you will not have to worry about this, but for this particular model, this model has a little bit too much structure. It's interesting, but it's not very pedagogical for the moment. So I will later simplify it. For this particular model, the Kirk-Teasing model has, this structure that for even times and odd times, it belongs to different universality classes. And for even times, it's kind of much harder. And we can only make conjecture that the spectral form factor is 2t plus 1. Nevertheless, what is kind of striking is that the model has basically no localization transition for any strength of disorder. I mean, if one is aware of this activity around many body localization, I mean, people would, for generic systems of this type, expect that if you have disorder and strong interaction, then for strong disorder, people would expect transition to many body localization. In this model, in particular, we can prove that there is no localization. Okay, so now just to make a partial summary before I'm going to, let's say the slightly more rigorous part, we found a simple, this was like a result of 2018. We found a simple local interacting model with finite local Hilbert space dimension with proven RMT spectral correlations, at least 2-point correlations at all time scales. Now maybe I can just ask what is the time that we still have. Okay, good, that's perfect. So yeah, let me just give you one more slide about this Kirk-Teasing model, and then I go to further simplify it, or let's say make it more abstract in general. But this model is still kind of cute because the way how this is just the first step of the proof that we made in 2018. But the main idea is the following. You can write a propagator. This is kind of obvious idea, right? In this quantum dynamics versus statistical mechanics picture, you can write a trace of the propagator as a statistical partition sum of a 2D statistical model. But in this particular case, this 2D statistical model is exactly classical Ising model in 2D with random fields which have positional dependence, but they are homogeneous in time. So, there is a 2D Ising model, but there are fields, and fields are depending only on position, but not on time, because the disorder is static. This model is not integrable, as it is known. Ising model without the field would be integrable, but with this striped field is not integrable. But what is kind of remarkable now is that what you can do is you can evaluate the trace of u to the t using what we call duality relation. Namely, you can, instead of using the row transfer matrix, you can instead of using the column transfer matrix, which is the propagator, you use the row transfer matrix. Now, this is not statistical mechanics. So the weights are not positive, the weights are complex amplitudes. And the column transfer matrix is the quantum propagator, which is unitary. But the row transfer matrix has no particular reason to have any specific mathematical property. but it turns out that it has exactly the same algebraic form as the Coulomb transfer matrix. I mean, both guys are exactly the propagators of the Kick-Teasing model, just with different coupling parameters. So there is a kind of identification of coupling parameters, J and B, in terms of J tilde and B tilde. And in general, J tilde and B tilde, which are the coupling parameters of the row transfer matrix, the so-called dual transfer matrix, are in general complex. But for the particular values of J equal to B equal to pi over 4, both row and column coupling parameters are exactly real. Actually, they are the same. They're equal to pi over 4. So the model becomes what we refer to as self-dual. So I mean, that has actually been pointed out a couple of years before in this paper by Boris Gutkin and company. And this is really something that can be explored. So I mean, the two propagators are given by the same model, and this means that also the other propagator is given by the unitary model. Okay, so now I'm not going to proceed with respect to Kick-Teasing model, but I'm going to further generalize, and I'm going to present a more general kind of theorem which addresses a group of models which share the same property. And that property we named dual unitarity, and you can formulate it much more generally. So the idea is just to go, I mean, to use the language of quantum circuits to write our Flocky protocol as a Flocky quantum circuits in terms of 2-qubit gates or 2-qubit gates. I mean, in general, you can have arbitrary local Hilbert space dimension. So for example, you take these 2-qubit gates, which map states I and J in the Hilbert space dimension of the, the local Hilbert space of dimension D, to states K and L. So this is like a D squared dimensional unitary matrix. And yeah, this matrix is required to be unitary, of course. But now what we require is that this matrix has additional property that is unitary also when you flip space and time. So when you require I and J to be in states and J and L to be out states, so we go this way, you also require to be unitary. So you define a U tilde as this, flipped, reshuffled matrix where you reshuffle, I mean, you have 4 indices, but you reshuffle across the diagonal. So you get these two unitarity conditions. You have the forward unitarity and what we call the dual unitarity. And you can ask yourself, of course, I'll ask in the following slide, but I will just tell you immediately how we form interesting models out of this scattering matrix, if you want. I mean, this is just, if you think of as kind of a scattering matrix, and out of this you build interacting quantum system. You define it again as a evolution, let's say, for 2 time steps. Time goes vertical now, and space dimension is horizontal. So now this would be like for two full time steps. 1/2 time step is just tensor product of 2-qubit gates. Then there is a shift. This shift I denote as pi over of 2L sides. Then I take another tensor product, and then I get an inverse shift, and so on and so forth. So it's like this staggered dynamics. U even times U odd. U even is just pure tensor product, and U odd is just shifted tensor product. Now, already from this picture, it should be clear that this is kind of symmetric. So I can also read it left to right. And I define a dual circuit, which would go from left to right, again, in terms of dual gate, which I denoted as U tilde in the previous slide. And immediately you have a formula, which is just writing partition sum over this 2D statistical-like model in 2 different ways. You have trace of U to the T equal trace U tilde to power L, one being row transfer matrix, the other being column transfer matrix. Anyway, so now you can immediately ask, I mean, whether this has any interesting examples. And of course, the answer is yes. I mean, actually, we can classify all possible dual unitary gates for qubits. Actually, to do that job for arbitrary Q dits, it's a very interesting problem in quantum information theory and related subjects. But for D equal to 2 is actually elementary calculation. So you just take a textbook parameterization of SU4 or U4 gate in terms of Heisenberg gate and 4 SU2s on the side, then 2 tensor products of SU2s on the side and the phase. And the only condition that is required, if you require this to be not only unitary but also dual unitary, is that the 2 coupling constants in the Heisenberg gate are equal to pi over 4. So which means that the dual unitarity enforces you that 2 parameters should take special values. So it's like codimension 2 manifold of a unitary group. a submanifold of a unitary group. So, of course, it's not a group. I don't know what kind of mathematical structure it is, but it has to do with, again, some concepts from quantum information like unitary channels, but I'm not going to get into that. But there are interesting examples. For example, there is a trivial example, which is the swap gate. Swap gate is just like the simplest non-interacting theory. It's a free theory. Everything just goes through. Or you can have integrable XXZ gate. This is just like an R matrix of 6 vertex model, but at particular values of parameter. One parameter is fixed and is equal to pi over 4. And the third most interesting example is the self-dual Kirk-Teasing model that I discussed earlier. Actually, if you take this complicated expression, then this dual unitary circuit becomes just Kirk-Teasing model from the previous couple of slides. Okay, so now, yeah, and then there's been kind of follow-up on these constructions by two groups from Cambridge, Austin Lamacraft, and again, a group of Tomaž and Boris Gutkin, who generalized this into kind of directions. But I'm not going to get into that. Okay, now let me just go to my final part, which is probably the most kind of mathematical, most rigorous. Let me just now present you with a simple theorem and try to give you the main idea of the proof. And so what we do now is basically to formulate at the moment what we see the most general setup in which we can prove random matrix spectral correlations in quantum lattice systems. So this would be a circuit which is given as a Floquet circuit in terms of clean gates, 2-qubit gates, which I denote, I mean, this is not very clear, but these are 2 different shades of red, which means that these guys could be in principle different 2-qubit gate. This is U, this is W. And then they are decorated by these single qubit gates, which are these circles, right? So these single qubit gates are there in order to provide disorder. So, I mean, we need some sort of disorder. We need to break translation invariance. Otherwise, we have to worry about translation invariance. We would have to separate that, and we don't want that at this point. So let's just introduce some disorder, and then you average over that disorder. Again, already from before, we remember that the strength of disorder doesn't really matter. So the results will be actually true at the end, even for 0 disorder limit. But what is important is that the limit of vanishing disorder is the very last limit in the calculation. So it has to be arbitrarily small, but finite. Anyway, so this is just a one-slide expression, which I'm not expecting you to follow because I later show a diagrammatic derivation of that. But the idea is that you provide a transfer matrix whose spectrum actually in thermodynamic limit dictates the behavior of spectral form factor. So now this is spectral form factor for system of size L and time t. Right? So this is like a partition, it's like a 2-copy partition function. I will see immediately what it is. It's like a two replica partition function of a system of size L by t, written in terms of these quantum gates. Yeah? Now the problem is, or the interesting thing is that now this, sorry, these colors are not too nice, and my computers, they look nicer, but you see, I mean, the problem is that now what you should see now, time is vertical, space is horizontal. So these gates are all the same. So there, of course, they can be staggered. So this gate can be different than this, but then you repeat. This is Floquet protocol, so you repeat it each time. You just, it's like a autonomous time evolution. I'm a periodically driven system, but you repeat the same protocol all over and over again. So the idea is now basically that, yeah, these gates are the same, but then on different side, you have a IID gate. So, I mean, independently distributed, so you can average over it independently. So the idea is that, you would now split this partition function into columns, and you would average each column separately. Because these guys are IID, so you can do this. Right? So this way of looking at things, as 2 replicas, and then putting disorder explicitly in this way, allows one to really compute explicitly averages over disorder. So that's what you do. So basically, you do another trick before that. I mean, I guess, some of you probably know this trick. I mean, it's probably also used in field theory a lot, but also in quantum information. It's called thermofield double representation, or in quantum information, people prefer to call it folded representation. So the idea is just to look at instead of looking at 2 copies, you look at a single copy, but now you double the Hilbert space. So which means that this propagator, you write it as U, but the one from the conjugate copy, you write it as U star, and then you just write it as U cross U star, and so the legs become now of the square Hilbert space dimension. So now this becomes of dimension 4, right? So now this is just a way of, diagrammatic, simplification. In the way, you just fold this guy on top of this, and then you see this red and blue, which are pressed against each other. You just represent by green. Yeah? And the same you do with this. The same you do with these single particle gates. Now you denote this gray or yellowish grayish gates like this. So now this immediately allows you to represent this transfer matrix in a compact way, right? So now this would be my column transfer matrix, or a transfer matrix, the so-called spectral form factor transfer matrix. Yeah? Okay, so now, maybe this time, maybe I pause a little bit and take some questions. I introduced some concepts, so maybe if there is some, now I go to the proof basically, but the proof will be short, so I'll just give you I've not even presented the theorem, but let me just give you a theorem and then the main idea of the proof. You see, the reason why I want to give you the statement of the theorem is that the kind of mathematics that we need to prove that is completely different than mathematics that people have used in classical chaos, in quantum chaos of single particle problems and Gutzwiller trace formula and all that. There was a lot of number theory there and this kind of stuff, but this type of algebra, this becomes now, this type of proof is completely algebraic. It's very different. At least it looks different to me, not knowing so much about mathematics. Okay, so what do we do? What is the statement? The statement is the following. Take any IID distribution of local gates. The distribution is kind of very, very general. The only thing we require is kind of smoothness of the distribution. So it should be non-singular over SU2. And any pair of dual unitary two-qubit gates U and W, I forgot to state also W could be arbitrary, which should be other than the swap. So the only thing you have to avoid is that they're not swap. Swap means non-interacting circuits, and then you don't have random matrix to it. Then the spectral form factor in thermodynamic limit. What we can do now is make statement in thermodynamic limit. So we cannot do finite size statements about finite size systems, but you have to do thermodynamic limit first. So which means that we can only make statements about very short time scales compared to the system size, compared to the Heisenberg time, for example. We cannot address problems of level spacings. We can address problems of short times, of what people call spectral compressibility, for example. So what is the statement? The statement is the following. Spectral form factor is given in terms of the dimension of the commutant of a simple set of operators which are formed of magnetizations, all possible components of magnetizations on a time lattice and coupled magnetizations, that is 2-point operators formed of Pauli variables. So all 9 possible coupling operators and 3 possible single-side magnetizations. These are the time magnetizations. So that magnetization is defined on a dual lattice, which has dimension of time, right? So in the meantime, we were kind of going forward from space to time representation, right? Because we use this dual transfer matrix. So the system size, which I didn't stress, was equal to T, yeah? And now we are looking at the system of size T, and T is finite. So we don't need any thermodynamic limits. This is like a quantum lattice system on a finite lattice of T sides, but we do thermodynamic limit. So we just need some sort of quantum Perron-Frobenius to be able to deduce problems of, the properties of thermodynamic limits from the spectrum of the transfer matrix. The transfer matrix itself is a finite matrix of 2 to the T by 2 to the T, or 2 to the 2T by 2 to the T. Anyway, so now again, this is just a simple set of operators, and you are looking for a commutant of this set, that is set of operators which simultaneously commutes with all these guys. And you want to know what is the dimension of the span of these operators, that is how many independent operators you have. And clearly, there is a minimal set of operators which commute simultaneously with all these guys, and these are the translations, because these are translation invariant operators, so they are T translations. So these T translations gives us T. But the crux of the proof is to show that there are no other. So we have to, okay. So if you give me 5 more minutes, I'll go through the main idea, really, really heuristically, but main idea of the proof, and you see where it comes from. What you have to do in order to show that there is no other. Okay, so first kind of step is to write this dual transfer matrix algebraically. So write it as a unitary times a kind of an object, which I like to think of it as a contraction or a non-expanding map, which is like an averaging map, another unitary, another averaging map. And these averaging maps are, again, can be factorized, but they are factorized to something which is like an exponential of the commutator. Yeah? And this is the PDF of the distribution of the disorder, of the local disorder. This is the measure on SU2. Could be hard measure if you want. That's probably the simplest, but it could be any smooth measure. And and this is the exponential of the commutator, yeah, written in this folded or thermofield double representation. Right. So now, so see, I mean, this is a nice structure because of dual unitarity. This U tilde and W tilde are unitary, and that's absolutely crucial. So that we have this decomposition of unitary times something which is non-expanding. That immediately tells us that the spectrum of this beast should be within unit disk. And then we have a simple lemma which teaches us when the spectrum, where the eigenvalue is on a unit circle. Namely, for any unimodular eigenvalue of this dual transfer matrix, we have the following properties. For any lambda, which is, first of all, we already explained you that all eigenvalues are within unit disk, but for any eigenvalue on the unit circle, the following has to be true. This eigenoperator, I'm now writing it as an eigenoperator, has to be simultaneously an eigenvalue of the unit of the unitary part. That's super cool. This has to be an simultaneously eigenvalue of the unitary part and an eigenvalue of the dissipating part. Dissipators. I guess I don't have really time and patience, your patience in particular, to go into more details, but you see, I mean, this factorization of this kind of Perron-Frobenius condition is absolutely crucial to be able to prove the gap. So now we know exactly what has to be true for the eigenvalue to be or the unit circle. If it is not true, we know that eigenvalue is inside, which means we know that we have a gap. Yeah, I'm closely done. It's one more technical slide. Okay, so that lemma is very simple to prove, but it's probably the most crucial one. Well, I mean, second most crucial in the proof. And then, of course, now we do the unfolding, which means we go back from thermofield double to the normal operator representation, which means now this operator is now written as a quantum channel, which means that this condition, which I wrote here, these three conditions, can now be translated in the unfolded representation simply as this commutativity condition. I already spoke about commutativity, but now you see it clearly. I mean, these two conditions, if you unfold it, this is just a commutator of W transpose, Hermitian conjugate, commutator with M, and this is just commutator of A with M. So these are these two conditions, and this is the first condition. Now we can do further. We can use the explicit parameterization of dual unitary gates in terms of two coupling parameters, which are the key parameters in our game, J and J prime, and arbitrary single particle gates, U1 to U4 and W1 to W4. And then we can rewrite these conditions. I mean, there is a kind of lemma you have to prove. It's not totally straightforward, but for any J prime, which is different from 0, which means for any gates other than swaps, this condition actually can be fulfilled only if phi is equal to 0, which means that we have, that if eigenvalues on a unit circle, we know it should be at 1. So there could be no other eigenvalue in a unit circle other than 1. And then this condition is equivalent to this kind of commutativity condition, which is basically the first line of the theorem. So you see, I mean, now basically we have a condition under which you have eigenvalue 1, but this can be satisfied by several operators. The question is, by how many operators is satisfied? She gives us that dimension. Second point part is just counting the dimension of the condition. Okay, now the last part is the third lemma, which we have to show. So now you look at this set of operators, right? And you look for now the measure of the commutant. And this we do just by brute force. Basically, we just show that representations of this algebra, which is generated by this set, and this algebra has the same commutant set as this set. And that representation of this algebra in the eigenspaces of two-side shift operator, the translation operator, periodic time lattice of these sides, are all irreducible and inequivalent. And that's enough to state that the only operators which commute with this guy simultaneously are the all possible T translation operators. Okay, so now that's in a nutshell the idea of the proof. And yeah, so I'm more or less done. I could discuss sort of several ideas which emerged in the literature in the last year or 2 years, essentially, around these dual unitary circuits. I mean, these dual unitary circuits seem to inspire a lot of people now, and they are discussing various kind of directions. I would mainly stress our recent work here published a couple of months ago in PRX, which is about doing perturbation theory around dual unitary circuits. I mean, if you can ask me, why should I care about dual unitary circuits? Because they are kind of fine-tuned systems. Yeah, the reason why I feel excited about it is that there might be some structural stability. So in a similar spirit that hyperbolic systems in classical chaos are structurally stable, I feel that these models, since they are kind of ergodic, and one should intuitively expect that the porosity is structurally stable, that maybe also the periodic expansions around dual unitary circuits might have finite radius of convergence, unlike perturbative expansions around integrable or free systems, which are usually very pathological. So we have one very partial result along this line in this PRX. I have no time to discuss it, but I just want to advocate it. But yeah. So with this, I would like to finish. So the point of my talk was just to present what I believe was the first exact result of spectral statistics of extended quantum lattice systems when thermodynamic limit is taken first. So this is basically the price we have to pay to take thermodynamic first. I mean, of course, statistical mechanics, this is the normal thing to do, right? But in chaos theory, people like to look at finite systems and you get time to infinity because that's how chaos is defined. Right? So then, in order to address all possible timescales in the problem, we would also be able, we would also very much need to understand finite size corrections that we show other timescales. And that seems to be kind of out of reach with the methods that I discussed in my talk. So for example, one very nice set of questions that someone has to get involved in is the eigenstate thermalization, which is behind all the current understanding of thermalization of many body interacting systems. Please, I would like to thank you for your attention.
Any question?
Okay, actually, a couple of questions. So one is, if I understand correctly, so you get this this limit of KT, which is T, which is one of the three the result for one of the three ensembles you mentioned.
Yeah, exactly.
This is because of unitarity, rather.
Yeah, exactly. So I didn't manage to mention that. Thanks for asking. Yeah, this theorem applies to the unitary case where the slope is 1. So there is no time reversal.
And can you get similar results for the other ensembles? Do you have
yes.
representatives of?
Yes, we have results for. We have partially complete result for the time reversal invariant case, which means we still have to assume something. So it's not a complete proof yet. And we have no idea what to do with the symplectic ensemble yet. Okay. I guess there should be also a way to do that. But
so in partial results, you managed to identify a model that is presumably
we have
for
all
which
the
you
steps.
Can presumably compute.
Yeah, the model is very simple. The model is exactly the same model, but you ask for some special property of this U on these two sides. I mean, this one has to be this one transpose. So that thing is self-transpose, right? It's a self-transposition symmetry, which is like time reversal, which is the time reversal in the many-body physics. And if you have that, then you have 2T, and we can almost show it. The point is that the Lemma 3 proof is not yet complete.
So why 2T? So you don't see the other saturation?
Well, the idea is the 2 is very simple because apart from
it was not exactly linear, the profile. It was 2T at the beginning, and then you had this.
Okay, no, that's of course, again, it is exactly linear because we have to do thermodynamic limit first.
Okay.
You see, that's the point, right? We do thermodynamic limit first. This is, of course, also, this is the kick teasing, which is orthogonal universality class. So this is also 2T, but the Heisenberg time is somewhere over there in the next group. So you will never see the bend over.
And the other question, can you comment a bit more about these first results you have about the structural stability when you perturb around the self-dual point? I mean,
yeah. So what we do there, we do something very simple, and we do a further simplification of this class of models. First of all, we don't look at spectral form factor because it's too complicated. We look at two-point correlation functions. We look at local observable, like spin-spin correlation function at time 0, x0, time t, x. And then we show for these dual unitary circuits that this correlation function can be non-zero only along the light rays, which move at speed 1, or light speed, if you want. And the reason for that is dual causality, because we have this dual unitarity, which means correlations can be non-zero only within the light cone, which opens at speed 1, but also at the dual light cone, which opens sideways at speed 1. So the intersection of two light cones is just two light cones. So the correlations can only spread at speed. That's the dual unity. And now we perturb it. So now we look at what happens when you perturb it, where the correlations actually merge. And this now we bound strictly. But we bound it for a class of circuits which are somehow half between random circuits, and clean models. So we do U1 random circuits. We take a random fixed direction and we average our random field. Then we get classical multiplications. And then this is like a perfect coherence, a perfect So then these quantum circuits are now equivalent to classical Markov chain circuits. And for that, we can write it. I will need 10 more minutes to explain it. Some conditions, but I'm still excited because it's the first kind of result. This kind of research is the first time. Very much.
Thanks.
It's hard to do anything more.
Any further questions?
So thank you for your very interesting talk. And this has been a quite long meeting. So I'd perhaps take an imaginary trip back to the first talk in the meeting and wonder if there might be some connection. And it's imaginary because I'm not sure that what I'm saying is complete nonsense. But the Fourier transform I talked about there involved a 90-degree rotation of pictures. And that
Sorry, can you repeat? I didn't hear you.
What?
Can you repeat the last sentence? I didn't hear you.
The Fourier transform I introduced in my talk involved a 90-degree rotation of pictures. And when I look at your pictures, it reminded me very much of that situation. And I showed that the Fourier transform was unitary and L2, but you were looking for a fixed point. So I'm wondering if this problem could be reformulated in terms of looking for fixed points of the quantum Fourier transform. And this analysis of the self-duality could be a question of a property of that operator F.
Okay, thanks for this remark. Unfortunately, I was not yet here, so I could not attend your talk. But yeah, so
But it's a very nice research problem because a conference where some new ideas from a different direction are influenced two of the speakers might be a very interesting conference.
Yeah, well, thanks for the question. I have no immediate response, but yeah, it's interesting too.
Some question, comment?
Thank you. My question is, does the dimension of the center of your algebra have some meaning unless it is one, or
which
by
algebra
chance?
you talk about?
So you have shown that the dimension of the commutant of some algebra is like the limit with L going to infinity. And what is the center of that algebra? And
okay, so it's a good question. We have not thought about this. I just don't want to bluff and say something now because it didn't look to be relevant to us. I mean, but that was really, this proof was super naive. I mean, what we did was really kind of a textbook brutal proof. I mean, we just wanted, we just constructed connection between two states. We just showed irreducibility by just connecting states in the same Fourier sector. So we take a translation operator. We give an eigenvalue, which is the momentum, and then we take two states with a fixed momentum, and we show that they are connected by application of string of operators. probably not the most elegant solution. So maybe you can use more fancy algebraic methods.
And also a curiosity, can you produce quantum chaos in lab? So can it be seen in some easy system?
Yes. That's now you're asking about single particle chaos, many body chaos. I mean, people have seen people have looked in single particle chaos. People have seen all that. Spectral statistics, they have measured. In the many body context, this has not yet become fully standard. But there are, for example, just a couple of months ago, people who played this Heisenberg Time simulator, they have realized this heat isn't true precisely the one which. And they computed correlation functions and they compared them. So the technology, quantum technology is now at the point that people can simulate this many bodies. So I think it's a really exciting point.
Thank you.
Okay, maybe we can thanks the speaker again.